Born and raised in the US, and this is my state where I grew up in the north on the border of Canada, surrounded by a bunch of lakes. But basically, I did all my education there, and now I live in Austin, Texas, where I work at Visa, the payment network company. And unfortunately, I cannot share a presentation about the work there because it's proprietary, but I want to share the work that I did during my PhD to give some indication of the type of work that I'd be interested in pursuing if I get invited to join as faculty at UOZG. So to give a general idea of the domain of work that I'm in, basically my work focuses around clinical decision support. And so the idea of this is mainly using machine learning models to assist a doctor in the hospital or in the clinic. And so, for example, when we're talking about assisting, it might be something like helping a radiologist who is going through different medical images like x-rays, maybe if or MRI, if we, for example, identify patients who seem to have especially severe tumors, maybe we might put their images on the top of the stack of patients that they might have to review that day, for example. Or maybe we want to identify conditions that are a bit trickier for human beings to identify with the naked eye. So this is the type of work that clinical decision support with machine learning aims to address. So with that, I'll go into my particular work. So my work is in advancing clinical outcome prediction with innovative multimodal and domain generalized AI for limited data. And I'll go through what all of that means. This is what the work that I did in the 5.5 years that I was at the Department of Computational Medicine and Bioinformatics at the University of Michigan. So I'm going to begin with an introduction and a motivation to my thesis question. And then I'm going to give 3 use cases on how we can address the challenges from the introduction. And we probably won't get through all of them. I probably only have time for the first 2 projects, but that's okay. And then we'll go into the conclusion. So let's start with the introduction and motivation. And if you have questions, feel free to interject. So I want everybody to think about the paradigm of a patient going into a hospital or a clinic and going to speak with a doctor about a medical condition that they have. Maybe they want a diagnosis or a prognosis from the doctor. The doctor will in turn try to gather as much information about the patient as possible. So, for example, the doctor might try to gather patients' biometrics. So then maybe they want age, height, and weight of the patients. They might try to gather some lab data. So, for example, blood or urine samples. They might want to get a patient history of this patient. So maybe they want to know about family medical conditions, and this can help inform about the conditions of the patient. Depending on the patient's symptoms, maybe the physician will also ask for things like a one-dimensional signal, like an electrocardiogram, or they might ask for some type of imaging, like CT or MRI imaging. So what we understand from this, and in doing so, the physician will take all the information and try to get a holistic view of the patient and create a sort of mental model in their mind about what the patient is like in order to come up with this diagnosis or prognosis for the patient. And so from this, we can understand that intrinsically, when going through a patient's medical conditions to diagnose or prognose them, we're seeing an intrinsically multimodal problem. So we are seeing a problem that is typically addressed in a multimodal way, with each of these being different modalities. Likewise, this is also a multi-domain problem. And what I mean by multi-domain is that the physician might see somebody of, let's say, for example, one race, like they might see a Caucasian person one time, but then maybe the next time they'll see someone who is, so this is a United States issue, so they might see an African American patient next. We know that there are some biological differences between African American patients and Caucasian patients. For example, we know that estimated glomerular filtration rate, which is the rate in which the kidney can purify the blood, that these measurements can be different between African Americans and Caucasian people. And as a result, we now have in the clinic, we have a separate measure of a recalibrated measure for African American patients. So that means we recognize that this is a multi-domain problem. In other ways, multi-domain problems can exist where we have, for example, patients who have undergone tests at different clinics. For example, MRI machines can be set up with different parameters, which means that images taken from different MRI machines can have different patterns in them. We can also note that for tissue samples, for example, they can be stained in different batches, which can affect the contrast of the image. We know when working with any type of machine learning models that when we have these type of variations in different external data sets that the model was not trained on, that this can often result in a lower performance of the model. But intrinsically, we know that in healthcare, this is healthcare is a multi-domain problem as well. So this brings up two questions. The first question is, how can we construct machine learning based multimodal models that can mimic these real world mental models that physicians have in their head to diagnose a patient? And secondly, how can we construct machine learning based models that can bridge these domain gaps that I talked about? So,
Elisa, quick question.
yes.
Is that okay that we interfere and ask questions or wait until the end before
Yeah,
we ask?
feel free to interject whenever you have a
All
question.
right. So my question is that, if you go back to, yeah, so I mean, can we treat these two questions independently, or is it that we should consider them jointly? The reason that I'm asking this question, that I've seen many past work and literature, they
Mm-hmm.
focus on, domain adaptation problems. There are many, I
Mm-hmm.
mean, it's a very old machine learning problem, actually. But with the advancement with the deep networks, they
Mm-hmm.
now started using, those large models to do the domain adaptation. So my curiosity is, if we, for example, develop multimodal models, foundation models in particular, and solve the domain adaptation problem, independently, and then we combine them, fuse them somehow. Or is it better to treat these two problems at the same time? So while we're solving the multimodal problem, we're also solving the, multi-domain problem. And I'm curious about, the answer about this question, particularly in the healthcare sector. Maybe it also
Mm-hmm.
depends on the application area. So what's your view on this?
Good question. So, I mean, in real life, when we're talking about real world clinical settings, both of these issues are serious issues that can affect the performance of the model. So ideally, we want to be able to address both issues in a clinical decision support model. However, they are also two intrinsically different questions that we're asking. So multimodal models are saying, can we add different modalities together? So for example, can we make a model that includes uh, this type of like MRI and CT in the same model? and also, I don't know, also like electrocardiogram. Can we, these are all different modalities. Can we add them together into the same model? That's one type of question. The domain question is to say, maybe my training data is a little bit different from my testing data because I got it from a different institution or something like that. Um, how can I make sure that my model is flexible enough that the performance doesn't decrease when I get this data from another institution? So these need to be approached in two different ways. They cannot be solved by the same method, but they should be ideally we can create models that address both issues.
Okay, I have a follow-up question, but I think I have to wait until the end. So I'm going to, you know, sleep on it until we finish the presentation. Please go ahead.
Okay. Okay, so in summary, we mhm,
Do you hear me?
yes.
So when you listed the two questions, you said that, okay, to construct a mental model for the physicians, right? But the thing
Mhm.
is that based on my experience, for example, for some diseases or for diagnosis, there is no consensus between physicians. Even just consider, for example, as a simple example, let alone the consensus. For example, for some consider vitamin B12, for example, the range for B12 is different in Turkey and in US. So this is just one simple example, even just in the blood marker. So, but in general, for many diseases, in fact, there is no consensus between physicians. So, in this sense, how can we take the uncertainty so that you can construct a well accepted model for physicians? Is my question
Uh,
clear?
good question. So I guess first of all, I should say that the typically the questions that uh, I'm addressing in these models are they wouldn't be, for example, a prescription for a patient. It would be more about whether or not there is some belief that this patient has a condition, and it's also the point of the clinical decision support models is never to replace the physician. So maybe the clinical decision support model will flag something in a patient's record and say, this patient is suspected of having something. And then at the end of the day, it's still up to the physician to decide based on their own knowledge about whether or not this patient has a condition or not. So uh, I think it's still up to the physician to decide based on their own experience. But the point of the model is more that it just flags, it assists the physician, not replaces them.
Okay, thank you very much.
Um, okay, I'm still thinking about that question. That's a good question. Um, Okay, yeah. So in summary, we understand that these mental models for diagnosis and prognosis are intrinsically multimodal and multi-domain. Therefore, we understand that there is merit to developing the multi-domain and multimodal models that are designed for compatibility in real-world settings. However, there are challenges, which I think people are recognizing already, to building these type of models. So for one, it's typically tends to be harder to collect and curate data sets the more variables you start to add. It's really difficult to get complete data sets. Um, when it comes to patients who are in the hospital and getting certain checks for some type of disease, sometimes, for example, physicians will order a test for a patient and sometimes they won't. It's difficult to assume, to create a model that assumes that any single patient will be getting a whole collection of tests. So we cannot create a model that expects that. And lastly, gathering data sets from different sources tends to be difficult, and we often tend to get small amounts of data from multiple centers. So the interest of this work is how do we incorporate different modalities or domains into models which can better fit clinical decision-making in real-world environments that have flexible needs. So one huge constraint that this work centers around is the constraint of limited data. So when we actually go to work with different hospitals or clinics, we tend to face this issue where they cannot really provide us a lot of data. So sometimes we have, for example, less than 100 or even less than 30 data points. That means it's difficult to employ a lot of these state-of-the-art models. So if we look at a lot of computer science papers, for example, they are using really large data sets with maybe hundreds of thousands of records, and they're all well curated, and they're creating these really complex models to address these problems. In real life, it's very difficult to get those to work because we don't have the sample size that we need to use those models. And additionally, it's very hard to get physicians to be interested in those type of models if the model cannot explain why it got the result that it did. So as a result, this often requires us to create some kind of creative solutions based on the needs of the client. So now we go back to the original questions. We want to construct multimodal models, but under the constraint of limited data. And likewise, we want to build multi-domain models under the constraint of limited data. So in this work, I'm going to present the 3 case studies where I apply these different models to limited data in clinical decision support. And these are just examples of different use cases. They are independent solutions, but the idea is that they can be applied in different situations or approaches can be combined. So let's start with the first project, which is a privileged learning project with dental data. And the title of this work is Predicting Osteoarthritis of the Temporomandibular Joint Using Random Forest with Privileged Information. And I'll explain what all of that means. So first, I want to start with reminding everybody of a standard machine learning paradigm. So in the standard machine learning paradigm, we have a training set and a testing set. At train time, we feed a model a set of features X and a corresponding set of labels Y. And we hope that we train the model well enough such that at test time, all we need to do is feed the model a set of features X, and it will provide a predicted set of labels Y. In a privileged learning paradigm, which I'm proposing now, we add a second set of features, X prime, which is available only in training and not in testing. And we call this second set of features privileged features. And the way you can think of this is like a teacher and a student. So the privileged features function as the teacher, and they are designed at training time to teach the model, who is the student, to better understand the relationships between features X and labels Y. And at test time, the teacher is no longer available, and the model is supposed to have learned the associations better by test time. So where is this useful? Well, it turns out that medical and research use cases often involve a lack of complete data. So as I mentioned before, oftentimes in real world clinical scenarios, some patients are receiving tests and other patients are not receiving tests. If we design a model that requires every patient to get a certain number of tests, no one is going to use this model in real life. So we need to be able to create a model which is flexible, and that's why we propose privileged learning. So privileged learning falls under this umbrella of these sort of 5 challenges of multimodal learning called co-learning, and it typically involves a lower quality modality. So this is going to be a set of features that are routinely collected. They are collected from every single patient, and so they are plentiful enough to be used in both training and testing. But the issue with it is that it tends to be sort of low quality. It doesn't give a very high signal. And then the second set of features is the high quality modality. So this is something that's usually maybe a test that's more expensive to obtain. And therefore the source data is not enough to be used in both training and testing. So we only use it in training. And this might be something like, for example, MRI. There are some examples of papers where the CT is the lower quality modality that every patient is tested with, and then some patients get a higher quality MRI, and then that is used as the privilege information. That's an example. So there are some common approaches to privilege learning. Most common is some type of neural network-based method where there are two networks and one is sort of constrained by the other through a loss function. The problem with this method is that it typically requires very large amounts of data. So usually images and something on the order of like hundreds of thousands. In this paper, they used hundreds of thousands of images. If we have a smaller sample size, we could use something like the SVM Plus. So SVM Plus was also created by Vladimir Vatnik, who created the support vector machine. It involves the development of a second hyperplane in the privileged space, which is used to predict the slack variables in the non-privileged space. However, there is a negative with this method, and that is that if you are using privileged information to predict error, like the slack variable, that means that you really need to trust that this privileged information is really, really high quality. That means it has to be almost like a gold standard information that you're getting from this privileged features. But in the real world, again, we have this issue. We cannot necessarily rely on like the privilege information to be of gold standard quality. In the clinic, there's not really many cases of something being gold standard. Usually physicians need to take multiple tests. They need to get multiple types of images in order to determine if a patient has some type of condition. So one test, one image is not usually a clear enough indicator by itself. So we need multiple low quality features to reach a reasonable prediction. Therefore, we want a traditional machine learning method for smaller sample sizes that doesn't require this gold standard privilege information. So we tried a tree-based decision classifier. So this model, which we call Random Forest Plus, is a tree-based method that incorporates both privilege and non-privilege information. And the good thing about a tree-based method is that at every time there is a node split, the model always chooses the feature that is the most indicative of the outcome, whether or not that feature is privileged. Therefore, this model does not require the privilege information to be gold standard. So the way that this Random Forest Plus model works is that first you create a random forest model from both the privileged and non-privileged features. So what you're seeing here is just one tree from this random forest model. Then we go through every tree in this random forest model, and we go through every node in the tree, and we identify which nodes are what we call linked nodes. And I will explain what a linked node is in the next slide. So once we identify the linked nodes, the goal is to replicate the activity of this tree up to that link node. So now we create what is called a scandent tree from the non-privileged features. And basically, we use the non-privileged features to try to replicate the activity up to that link node. And so if we see the link node as separating into the left child or the right child, we can think of this in a binary way as distinguishing 0 or 1. And then we can use this scandent tree to create features based on these linked nodes. And these are binary features that go back into the original data set. And then we create a random forest from those features plus the original features. And we call those new features the feature transforms. So this is how the RF plus model works. So I talked about going through, iterating through the trees and determining which nodes are the linked nodes. So how do we determine a linked node? A node is a linked node if, one, it is a root node. So this here would be a linked node because it's a root node. Number two, if the node feature is privileged, but the parent's node feature is non-privileged. So here, this P stands for privileged. So this is a linked node because it's privileged and the parent is non-privileged. Or third, if the node feature is non-privileged, but the parent's node feature is privileged. So if we imagine that there is a split at this node here, and the feature is non-privileged, but the parent is privileged, so therefore this would be a linked node as well.
Elisa, how do I know the node is privileged or non-privileged?
So it's privileged if the feature at that node, the feature that splits the node, if that feature is a privileged feature. So we predefine at the beginning, what is a privileged feature, what is a non-privileged feature.
I see. So you're imposing the data structure where you have two categories inside the data onto the graph structure where you label the nodes with privileged and non-privileged based on the data. So you learn kind of the structure from the data. Is that a good assessment of what you're doing, or?
Yeah, I think maybe I'm understanding you. Yeah, we in the beginning we take the whole data set. We are trying to make a tree with the privileged features, but actually ultimately we don't want privileged features to be in the final model because the whole concept is that at test time the privileged features are not required anymore. So what we are trying to do is we want to use non-privileged features to replicate the activity of the privileged features wherever the privileged features are used, basically. So like there's one used here. So now we want to use non-privileged features to replicate its activity.
No, I understand that. I'm just curious that if the privileged, non-privileged, being privileged or non-privileged is part of supervision, or is it something that we generated throughout learning?
So we predefine what is privileged or non-privileged based on, so you'll see an example like the example of when I go through it, but basically the non-privileged features are the features that are routinely collected in the clinic. Like we want them to be ones that we know that every patient is going to get. And then privileged features are going to be additional tests that we don't expect every patient's going to get. So that way at test time, we never need a patient to undergo this extra analysis. They just need the routinely collected information to determine the outcome. We
All
are
right.
using, oh
Yeah,
yes,
okay. Okay, thank you. Got it.
okay. So the aim of this study then was to apply this random forest plus to our data on temporal mandibular joint osteoarthritis, also known as TMJ-OA. And we wanted to see a second thing. We wanted to add some interpretability. We wanted to see if we can assess which of the privileged features were most helpful in determining TMJ-OA. So let me give you an idea of what TMJ-OA is. So first of all, this here at D is a temporal mandibular joint. It is the joint that attaches your mandible to your skull. Osteoarthritis of the temporal mandibular joint falls under the umbrella of osteoarthritis, which is the second most common musculoskeletal condition next to lower back pain and accounts for about 15,000 cases per year. When a patient has TMJ-OA, they typically have some clicking of their jaw and it can get locked. This is characterized in these CBCT scans by a flattening of the lateral condyles here, a decrease of the joint distance, which is also represented by here, these, and some type of disfiguration of the articular fossa region right here. So when a patient is suspected of having TMJ-OA, they are given a short clinical questionnaire where they're asked questions like, how wide can you open your mouth? Do you have muscle soreness, etc. So every patient is given this questionnaire. Further analysis can be done with CBCT scans, which are these, of the temporomandibular joint, but this is less common. In our study, we obtained data from 97 patients with the CBCT scans. We were able to extract radiological features from the lateral condyles and the articular fossa regions, as well as the joint distance. And we were also able to obtain protein, saliva, and serum tests. So these are not tests that are typically given to patients at all. So the aim of this was to apply our RF plus model to our data on TMJ-OA. So for the non-privileged features, we decided to include just the baseline questionnaire, which is asked of all the patients. And as our privileged features, we decided to add the radiomic features, which we got from the CBCT scans, and the protein measurements from serum and saliva. And so,
Elisa, sorry, here you said that there are 97 patients with CBT scan, but I see only 49 patients in the total sample. So for questionnaire, how many patients this non-privileged features, how many patients has been gathered compared to the privileged ones?
So every patient, so in this data set, every patient of the 97 patients had the questionnaire given to them, even the control patients. So 49 of the 97 patients had TMJ-OA, but all patients, because this is a research project, all patients were given the questionnaire and all were given the scans of their jaw and the serum tests.
For the brain set, basically, everyone has privileged features as well.
Yes. For this test, or for this, I guess, research study, all the patients had those scans available, but at test time, we just omit those to assess the score. So if the patient is included in the training set, we will include their CBCT scans and their lab tests. But if they're in the test set, then we don't use those. Okay. So basically the workflow is that, so I used the 5-fold cross-validation, also used 200 times out of bag method. So there were 2 methods used. This workflow is like this. So first, we did a feature selection via logistic regression for the privileged features because there were so many of them. So to narrow it down, we did that. Then we ran the random forest plus model. And after this test is complete, we did the post hoc feature analysis. And then in order to determine the feature importance, so we wanted to see which of the privileged features were most important. We we looked at the final tree. So if you remember, the final random forest model has no privileged features in it, but it has those feature transforms based on the scandent trees. So we iterated through every node in the final random forest model, and we saw which of those features were the feature transforms. And if they were, we went back to the original link node that it's based off of, and we looked at the feature at that link node. And then we scored the feature importance based on the frequency of the node features that ended up being selected. So here's the results. So the out-of-bag results and the leave one out cross-validation are similar. So I focus on this. There are numbers here. So the baseline model is a model where we only use the questionnaire. The random forest plus model is where we use questionnaire plus CBCT plus serum and saliva for training, but only questionnaire for testing. So we can see that our random forest plus model provided some marginal gains over the baseline model. We also see that if we create a model which is only based on the privilege information, we can see that the model actually performs worse. And so one thing that we note as well is that we verify with this model that even if the privilege information is not a gold standard quality, that we can still see gains with our random forest plus model. Next, we looked at the feature transforms and the feature importance of the feature transforms. We also verified this through an independent analysis with the statistician who didn't see my results, but they got basically similar results. We found that the most important features are how wide you can open your mouth, how old you are, joint distance, which we know a priori to be important, and also several features from the lateral condyles. So in conclusion, what we did was we created a privileged learning model for TMJ-OA, where routinely collected variables were considered non-privileged information, and the CBCT scans and protein serum saliva tests were considered privileged information. And we showed that random forest plus this privileged learning model can provide marginal gains to a predictive model, even if the privileged information is not of gold standard quality. And second, we determined which features were the most important for TMJ-OA diagnosis. And this is unique because no other privileged learning models that we're aware of is able to interpret specific privilege features which are important to the model's performance. Okay, so I'll pause for questions and then go to the next one because it's a story.
Elisa, do you hear me?
Yes.
I'm sorry, I have some internet connection problem. Okay, thank you very much for this very nice presentation. I have this question. So I just wonder whether your framework is applicable to cases where you have more than one disease, so that there is coexistence of symptoms, and symptoms may come from two different diseases. And in fact, on top of those, you can add the following situation, when you have a disease, you get stressed and you have some anxiety, and they also induce additional symptoms. So in such a complicated situation, will your framework work, or does it need to be extended?
So this exact framework would need adjustment if we want to talk about comorbidities as well. But the random forest is actually really good model if we are interested in also accounting for those comorbidities. So for example, if this person also had like known, I don't know, like osteoporosis, then maybe that could be really informational. Or if they have like low calcium levels, or I don't know, some other maybe some other conditions that could be added into the random forest plus model, and it would actually be a good addition to the model. But currently I think this model as it is right now, it doesn't really account for any other comorbidities for a patient, but I think this is a good addition to the model.
Okay, thank you very much.
Okay, I'll continue to the next one. This one's more of a story. So the next project is a domain generalization, is where we look at domain generalization in eye data. So this project is a prediction of post-operative refraction after cataract surgery. So I will describe what these are. So first of all, this study is about cataracts. So cataract is one of the leading eye conditions for aging adults. It's categorized by a protein buildup in the lens of the eye, and it's responsible for nearly half of all blindness worldwide. When a patient has cataract, the typical treatment for it is a removal of the natural crystalline lens and a surgical replacement with an artificial lens, as shown in this image. So when the surgeon places the lens into the eye, they need to determine the correct power of the lens to place in there. And you can think of the power of the lens as something similar to like a glasses prescription or a contact lens. You need to put the right power into the eye so that the patient has clear vision. And so how do they determine the power of the lens to put into the eye? So they use something called an IOL power formula. So IOL is intraocular lens power formula. So one example of one of these IOL power formulas is the SRKT formula. And so what you would do if you were the surgeon is you would input different patient biometry, that's different measurements of the eye, some demographics, which is just the gender of the patient. And then you would put the power of the lens that you want to implant into the eye. And then the formula will output what it believes the post-operative refraction will be. So that means what it believes the power of the patient's eye will be after you put the lens into their eye. So for example, if you are the surgeon and let's say you put in patient information, you say, I want to put a 21 diopter lens into this patient's eye. What will the patient's eyesight be after the surgery? The formula might, for example, output 0.23 diopters. If the output prediction is 0.23 diopters, this is good. Ideally, we want, so these are the power prediction errors. Ideally, we want 0 diopters. That means a patient has 20/20 vision. If the error is less than 0.25 diopters, it means they probably don't need glasses. They are doing well. Typically, the surgeons will aim for less than 0.5 diopters. They consider that a successful surgery if it's lower than that. If the error is over 1 diopter, this is considered really bad and kind of like a failed surgery. This patient will need glasses after that. So I talked about the SRKT formula, but there are actually many different formulas that a surgeon can select when they are trying to calculate the power of the lens to put in the eye. A couple of years ago, the lab I was working in, a student developed a machine learning based IOL power formula, which they called the Nalasami formula. And they determined that this machine learning based method was more accurate than any other IOL power calculation formulas that they compared to. But there are some caveats to this. So firstly,
Elisa,
yes.
are these formulas a closed form formulas?
Oh, closed form formulas?
Except the neural network based one.
Good question. I know that I would say up to here. I know these four are closed formulas. These three are proprietary.
I see.
So I don't think they are. In fact, I know this one is some machine learning based one, so I'm
Ah,
not
I see.
sure about
I
this,
see.
but I don't think Barrett is. They have to use some type of simulations, I believe.
Okay. And in the follow-up question, how do you know, your method is better than the rest of the others?
So yeah, good question. So yeah, let me describe this graph. So this graph is looking at, so basically you can go online and you can input the same patient information into these different formulas. And then they will output a prediction of what they think the patient's refraction is going to be. And then once you do the surgery, you test the patient's actual eyesight, and then you can calculate the error. So we have a true, the true postoperative refraction of our patients, and we can look at what the predictions were for all of these models, and then we can assess the error. So if we're looking at the red bars, that means the error is less than 0.25 diopters. This tan is between 0.25 and 0.5 diopters of error. This is 0.5 to 0.75 diopters of error. Dark blue is greater than 1 diopter of error. So we can see when we compare the true postoperative refractions to the predictions, we find that this Nalisamy formula had the lowest error compared to the predictions from the other models. The caveats, though, of this Nalisamy formula is that in this paper, this formula was only trained and tested on data from the University of Michigan Kellogg Eye Center. So all the patients came from the same demographic. And all these patients were also implanted with the same exact lens, which was the Alcon SM60WF lens. So it's very specific to this demographic and this lens. So the question that I was posed with is, can we use this formula, the Nalisamy formula, to predict postoperative refraction in different patient populations which are implanted with different lens models? So these are the data sets that we had to work with. So basically, we had this data set from the University of Michigan. This is the same data set that the Nalisamy formula was trained and tested on. So it is this SM60WF lens from Alcon. And then we had 3 different data sets from Chennai, India. And one was this Indian population implanted with the same lens. And then we had this Indian population who was implanted with 2 different types of lenses. And it should also be noted that we don't have a large enough sample size to train a model with all of these different samples together. Okay. So out of the bag, I just tested the Nalisamy formula on these different lenses and different patient populations. This is the performance on the SM60WF lens in the US population. This is what the formula is trained and tested on. This model outperforms the other IOL power formulas. However, once we switch to a different population, even though it's the same lens, we see that the formula starts to lose performance. In fact, it's not performing as well as some of the other formulas. And when we changed the lens as well, this formula did really bad. So basically, we identified a limitation of this model. The model performed the best with the lens and the population that it was trained on. It performed moderately when we changed the population but keep the same lens. It performs poorly on different lens, different population. So the next step for me is to understand why is the model performing poorly. And to do that, it's important to look at what the features are in this model. So all intraocular lens formulas are given these patient eye measurements. So they take measurements of the eye, such as, for example, axial length, lens thickness, corneal thickness, etc. And these are the features which I expected to be the most important features in this Nalsami model. But that's not what I found. Actually, these eye measurements were not really that important at all in this formula or in this model. Actually, what ended up being the most important in this model was other intraocular lens formulas. So they were also fed as input into this model, and these measurements ended up being the most important for predicting postoperative refraction. So this is a problem, and this is a problem for a specific reason that I did not yet describe, and that is if we go back to these other IOL power formulas. I mentioned that you have to include this patient's information and the lens power, but you also have to include something called an A constant. And the A constant can be thought of as a correction term to these formulas. It is an empirical number. It has no units. It requires a lot of data to optimize this number. It differs by lens model and population, and it is different for each formula. So for example, I mentioned these other IOL power formulas. They all have their own A constants as well. And so what we can conclude from this is that the most important features in this model require an A constant, and it's reasonable to assume that this makes it difficult for the model to generalize to other populations and lens models. So ideally, we want to create a model which is less dependent on A constants. Oh, I need to give a side note on A constants. So also remember how I showed you this chart. So again, these are different error rates. This is less than 0.25 diopters. This is 0.25 to 0.5 diopters, for example. This is the same lens, but a different population. Well, I used a different set of A constants than the University of Michigan data set. And I got this set of A constants online from a publicly available library of empirical A constants. And this library has the different A constants for each brand of lens, and in some cases for different populations who use this lens. So for example, there is an Indian A constant for this lens, and there's an American A constant for this lens.
So Elisa, do I understand it correctly? A constant is a function of lens and plus population, right?
Yes.
Or is there any other dimension that I should think about
honestly, probably yes. Like the A constant is sort of this catch-all for every error that could possibly, like every factor that could possibly be missing from these formulas. Like these formulas are really basic. Like you can think of them as like linear regression formulas. And the A constant is a correction term that kind of just readjusts the line. So it sort of is a catch-all for everything that's missing from that equation. And that's what makes it really a number that you don't want in your formulas.
Got you. Okay.
So these empirical numbers differ from the A constant that the manufacturer gives you. So also, when the surgeon gets the box from the manufacturer of this lens, the manufacturer also gives the surgeon an A constant number. This A constant is different usually from the empirical number, and it's just the manufacturer's sort of best guess of what the A constant should be. But you'll find that this number can dramatically change the results of a model's prediction. So here we are looking at this US population that the Nalsami formula was trained and tested on. On the left is the model, are all these models if we use the empirical A constants, and on the right is the model's performance if we use the manufacturer's A constant. So we can see that in some cases, so for example, with this Nalsami formula model, if we use a manufacturer A constant, the performance dramatically decreases. And this is also generally true for these other formulas as well. The manufacturer A constant is not very good. Okay, so going back to the problem, we made a discovery. We learned that the Nalsami formula is sensitive to changes in population and lens model because of a dependence on this so-called A constant. So now the question is, how can we redesign this Nalsami formula for domain generalization to drop dependence on this A constant? So the first thing we did is we went back to the model construction. So this is a general diagram of what the Nalsami formula actually is. It's just an ensemble model of 5 different machine learning based regression tools. And each of these output a regression prediction to the stack regressor, which is just a linear regression, and that outputs a single prediction that becomes the final postoperative refraction prediction. So what we decided to do, the first thing is we decided to add an additional artificial neural network. And the reason we did that is because we believed that an artificial neural network out of all of these models is the most capable of being able to take the patient biometric data and doing mathematical operations on them. So we believe that there needs to be more representation from this type of model in this framework. So we added another one. The second thing we did is we go back to the 5, these 4 other models which are in this framework. And these are all really dependent on feature engineering. So we focused a lot on revamping the feature engineering. Because you cannot do mathematical operations on the features that come in, you basically need to provide as much signal in your features as possible. So you need to create some salient features. So we went through all the literature on different IOL power formulas and added 33 new features. We also removed 9 features which did not seem to contribute to the model at all. 4 of these new additional features were other IOL formulas that were not based on an A constant. 2 of these were modifications that I made of this original Barrett formula, which came out in 1987. This was a paper published by an ophthalmologist, Graham Barrett. The Barrett formula is no longer used, but it was replaced by the Barrett 2 formula, which is one of the most popular IOL power formulas now. However, we don't know how that one works because it is proprietary. But one reason why this formula is no longer used is because it assumes that the lens that is placed into the eye contains only one convex lens. But nowadays, the lenses that are in the eye are biconvex. The light enters from here, it refracts once, and then it refracts another time when it exits. So basically, we made modifications to the formula, which is based on a biconvex lens. It requires 2 new user inputs. One is the refractive index of the lens, which is available on the box. The second is some knowledge about the equiconvexity. So the equiconvexity affects the placement of the lens planes, so where the light will refract. there are two typical types of lenses that we see. One is the anterior asymmetric lens, which is like the Elcon lens, where the anterior lens is larger than the posterior lens. The second is the equiconvex lens, where they are the same size. So this is a modification we added. So here's the result to summarize. So this is our new method under the US population with the Elcon lens. We now see that on the left is the empirical A constants, on the right is the manufacturer A constants. We can see that previously the Nallasamy formula was really unstable when we switch between A constants, but we now see that there's much more stability between them. The model also maintains most of its performance. When we look at the feature analysis of which features are most important in this model, we see that there is some decrease in the importance of some of the A constant based formulas, and we see more increase in the importance of non-A constant based features. We also see the two derived features that we calculated to be among the top 12. So now we look at the Indian population with the Elcon lens. We see an improvement in performance of our method over the Nallasamy formula. It outperforms the other methods that we are looking at, and it's stable across manufacturer and empirical A constants. There were two other lens models that I mentioned. One was an equiconvex lens, one was not. Here's the performance of the non-equiconvex lens. It still outperforms all the other models. This one didn't have empirical A constants, so we don't have that comparison. And then this is the equiconvex lens. Even though it doesn't actually outperform all of the other models, but it outperforms the Nallasamy formula, and it holds steady over the change in A constants. We also looked at the correlations between our model's results and the true postoperative refractions. And we found that our model and the Nallasamy formula, both of these had the highest correlations between our predictions and the true postoperative refractions. So in summary, we found that our model demonstrated competitively lower prediction errors compared to the other IOL formulas, but it was also more robust and stable across various A constant sets. Even if you only had the manufacturer A constant and you don't have the empirical one, the model can still provide fair results. We were only able to test on 3 different types of lenses, but we were able to demonstrate with those 3 lenses that the model is generalizable to other standard biconvex lenses, as long as you know a refractive index and you know a little bit about the shape of the lens. I'm going to actually skip this because I feel like I already went over, but I just want to summarize. Again, our question was, how can we construct these multimodal models under limited data? So we showed one example with using privilege learning. So we don't require some features at test time. And we use the random forest model to provide accurate results, even with a small sample size. And also, how can we construct machine learning based models that bridge domain gaps with limited data? So we also showed a sort of investigative story of domain generalization in cataract surgery. So we basically changed the framework. We also revamped the features, and we looked at reducing the dependence on A constants. Yeah. And for future directions, I just want to refer to a survey paper that I wrote where I talk about 5 challenges of multimodal learning: representation, translation, fusion, co-learning, and alignment. the focus of what I want to do in my work is to continue to address clinical decision support using multimodal solutions that also address one of these 5 challenges. And yeah, those are my publications.